Okay, so this week we're going over Lab 9, greenhouse effect, carbon dioxide concentrations and temperatures. It starts on page 74 in your lab manual. So we're gonna watch 3 videos and then you will answer a couple questions on page 77 and 78 and 79, just about greenhouse effect and the atmosphere and about the lab. 2 of the videos are just kind of instruction about what greenhouse gas effects are and why it happens. I'll go over it a little bit, but not too much because the videos will show you a lot more. And then the other one will be a demonstration of the actual experiment that you would have done in the lab today. So what you'll be turning in, I'll go over this again later, but the deliverables for this lab is going to be scans of pages 77 through 79, and then you're going to have 1 Excel graph, and you'll be able to find all of that right here. Oh wait, no, hold on. Lab 9, not Lab 8. So it'll be these 3 videos, and then here's where you'll get your data sheet. So greenhouse gas effect, I'm sure everyone's heard of that. Basically, you'll see in the first video, it goes over it pretty nicely, what exactly happens, but solar radiation comes down, energy, it gets reflected somewhat by the atmosphere, some of it's absorbed by the ground, some of it's reflected by the ground, and then the molecules in the air is mostly made up of oxygen and nitrogen, which are both, I don't know how much chemistry you have, but I won't get too deep into it. But the reason that greenhouse gases like CO2, H2O, ozone, which is O3, they all can reflect things because of their bond angles. If you look on page 74, you can see oxygen and nitrogen, they're both diatoms, which just means that in natural states, they're going to bind with each other. Oxygen with a double bond, it looks like this. Nitrogen has a triple bond. The more bonds you have between one atom to another, it just means the shorter and the stronger they are and the less that they're going to be able to move. This is CO2. It's got 1 carbon double bonded with 2 oxygens, and this can shake back and forth. You'll see in the second video kind of how that does that. H2O is the exact same shape as this. The electrons aren't shared equally, so it forces this bent shape. And once again, it lets the molecules toggle back and forth. So you'll see how that happens. And that's just kind of how these greenhouse gas effects or gas molecules can reflect the infrared heat energy back towards the earth. So I'll just show you the first video. Let me make sure that you'll be able to hear it.
Hi, it's Mr. Anderson, and in this video I'm going to talk about the greenhouse effect. And when you talk to people about the greenhouse effect, they tend to be pessimistic, but we really need the greenhouse effect on our planet. And so let me throw the sun out here, and then let's throw out the Earth. And so we're going to make this a black body. What does that mean? We're going to make this an object that absorbs all the light that's coming from the sun. So this is just theoretical. And so the scale is all wrong. The Earth is too big. It's way too close to the sun. But if we were to just imagine the Earth as a black body, we should have a temperature of around 5.3 degrees Celsius. Now you know this, if you're on the moon and you were to look back at the Earth, we can see it, so we know the Earth is not a black body. We know that it's reflecting a lot of that light, about 30% of it. And so if we were to take into account that reflection of light, then the Earth should be around negative 18 degrees Celsius. And this would be awful. All the water on the planet would be frozen. There's no way that life is going to be able to exist. And so what else do we have to add to this model? We have to add an atmosphere and the greenhouse effect. And what that does is it keeps heat close to the Earth. And so we should, and we do, have a temperature of around 14 degrees Celsius. And so that difference is just accounted for using the greenhouse effect. And so we really need the greenhouse effect. Where does it get its name? It comes from the greenhouse. And so how does a greenhouse work? Well, visible light is going to be coming through the glass itself. And so it's going to be reflected back, and it just goes right out of the greenhouse. You can look in a greenhouse and you can see things inside it, so you know the light is being reflected. Now let's look at light that is then converted into infrared radiation or heat. What happens to that? Well, when it hits the glass, some of it is going to be lost as heat to the environment, but some of it is refracted or bent back into the greenhouse. And that gets bounced around, we lose some of it, and so that heat is going to stay inside the greenhouse effect. Now, if we can limit convection or the movement of the air, then we can keep all that heat inside a greenhouse. It works a little bit different in our atmosphere. And so how does our atmosphere keep heat close to it? Well, let's look at what the atmosphere is made up of. It's mostly nitrogen, like 78% of it. We've got about 21% oxygen. We've got around 1% argon. And then there's this really tiny little black band right here, and that's going to represent everything else. Now, water can vary, and so we could have up to 4% of the atmosphere dealing with water, but we still have this really faint line here that you can't even see. And so what's inside there? Well, a lot of the greenhouse gases are inside there. And so what does that list contain? It contains water vapor, but it also contains carbon dioxide, methane, nitrous oxide, ozone, which is actually really important, and then chlorofluorocarbons, and a lot of those are produced by humans, and these are all greenhouse gases. And so how do they hold heat in? Well, I'm going to use a simulation to show you this. This is a PHET simulation, and so I'll put a link in the video description down below. I would encourage you to go there and check it out, but let's take a look at that. First thing you should look at is how visible photons and infrared photons interact with the gases that we're going to find in the atmosphere. And so in this simulation, we've got methane, we've got carbon dioxide, water vapor, nitrogen, and oxygen. So let me throw all of those into just a fake atmosphere. On the left side, we've got an emitter that is going to give off either visible radiation, light we'll call that, or infrared radiation. And so what do you think is going to happen when we hit these all with light? Assume that molecules can't move around. Well, if you watch this as the light moves through it, nothing happens. In other words, it's not affecting those molecules at all. Okay, so what happens if we turn off light and then we turn on infrared light? So this is going to be infrared photons. You should make predictions about what you think is going to happen. So let's turn this on now. So you can see that some of that heat is being bent and refracted, and it's actually coming back from where it was. Can you see a pattern of what molecules are vibrating? So let's see, I see methane is definitely vibrating right here. What else do we see? So there's another methane. I see carbon dioxide, so carbon dioxide right here is moving. And what's the other big one that's moving? That would be water. So the water's vibrating and re-emitting that heat. If you look at things like nitrogen gas or oxygen gas, they're unaffected by heat. And so what does that tell us? Well, if our atmosphere was just made up of nitrogen and oxygen, light would come in, heat would go out, and we would have a really cold temperature on our planet. So we need these greenhouse gases. Let's take a look at how that affects our atmosphere at the level of the atmosphere itself. And so what I've done is turn back the clock a little bit. So we're in the last ice age. This shows our greenhouse gas compositions. Now this is thousands of years ago, and so you might think, like, who was keeping track of greenhouse gases at that point? Well, nobody. If we look at ice cores, what you'll see is there are layers in the ice cores where we had summer, winter, summer, winter, summer, winter, and so you can count back and figure out how long ago it was. And then little bubbles of the atmosphere are trapped in the ice, so we can take out a section, we could add it to a mass spectrometer, and we can figure out what's the composition. So we can see how much carbon dioxide, methane, or dinitrogen oxide, these are all greenhouse gases. Water, actually, we don't know because, I mean, the ice is water. But we can figure out what the composition was back then. And so what did it look like back then? We had a lot more ice for sure. And so watch what happens as a visible photon hits the ice. It just bounces right back again. And so as visible photons hit the ice, it's reflected back into space, so we're not getting that heat energy. If you look at photons then that are hitting the soil, they're being converted into infrared photons, and so we think of that as heat. And so as they move up, they're doing this kind of crazy dance. Some of them get refracted, some of them get bent back towards the atmosphere, and some eventually move off into heat. But since we have a low level of these greenhouse gases, we're not holding much of them to the planet, and so this area we would have a temperature of around 34 degrees Fahrenheit. Let's move forward a little bit. So take a look at these greenhouse gas compositions. I'm going to move forward to 1750. And so what do we see then? Higher amounts of greenhouse gases. So these were actually recorded by people. So we have higher amounts. So what do we see now is an increase in temperature. What's causing that? We're holding more of that heat close to the planet. What happened when we got rid of all that ice, more of that light, instead of being bent back into space, it's actually being absorbed as heat. It's normal to see changes in the greenhouse gases, but let's look as we move forward from 1750 until today. And so especially look at these numbers right down here as we move forward. So we see huge increases in those greenhouse gases. Again, if we go from carbon dioxide, it was 280. I just checked today, it's well over 390, I think 397. We're pushing 400 parts per million. We're seeing huge increases in the other greenhouse gases, if you look at methane, for example. And so what's happening with that is we're seeing increase in the greenhouse effect. And a lot of this is caused by greenhouse gases that we're putting into the atmosphere. And so the industrialization has really increased amount of those greenhouse gases. And what we start to get is greenhouse that kind of builds on itself. Let me talk about two ways that occurs. So for example, if we go back to the Ice Age, what happens as we start to melt the ice on our planet? Well, as we melt the ice on our planet, then there's more light being absorbed by the planet, and so it's going to increase that heat. Another thing that happens up in the north, that as we heat the permafrost, it releases a lot of methane. What happens with that? Well, it heats the earth more, so it releases more methane. Or you could think of the oceans, what's happening as we heat it up, then more water vapor moves into the atmosphere, which causes the earth get warmer, and so that's going to heat up the ocean even more. And so that's the greenhouse effect. Again, we need it, but man-made greenhouse effect is really causing global climate change that we're going to have to deal with over our lives, and I hope that was helpful.
Okay, so that was the first one. And then this next one is just going to go a little more into the molecular geometry and the unequal sharing of electrons. This one is a lot shorter as well.
The Earth and the Moon are basically the same distance from the Sun, yet temperatures on the Moon average an unlivable -18 degrees Celsius. And even deadlier, they range from -170 Celsius during lunar night to 100 Celsius at lunar noon, regularly exceeding both the coldest and hottest temperatures ever recorded on Earth. And while the days and nights on the Moon are about 14 times longer than those on Earth, our planet's relatively fast rotation isn't what spares us from those loony temperatures. What protects us is our atmosphere. By day, it serves as a shield, blocking out the most harmful and energetic of the sun's rays and about 1/3 of the less intense but visible light. At the same time, it traps the infrared radiation, aka heat, radiating out from Earth's sun-warmed surface, keeping us from freezing solid at night. In order for our atmosphere to absorb any kind of radiation, it needs to have some electrically charged particles for passing electromagnetic waves to push around. And most of our atmosphere is made up of gas molecules that don't have an electric charge. They all have a balanced number of positive protons and negative electrons. But some molecules hold most of their negatively charged electrons closer to one side, lending them a lopsidedness that can jiggle back and forth to absorb the energy of incoming infrared rays. For example, water, ozone, and nitrous oxide are all electrically lopsided, so they all absorb infrared radiation. Then there are gases like carbon dioxide and methane. On paper, neither molecule looks lopsided, so it doesn't seem like they should be able to absorb any radiating heat. But in reality, gas molecules aren't motionless. They crash into each other billions of times per second, knocking each other in different directions and also into different modes of rotation and vibration. And it turns out that both carbon dioxide and methane spend most of their time shaking it in electrically lopsided ways, allowing them to absorb infrared rays and help insulate the Earth. Even though many different kinds of molecules can absorb infrared radiation, the vast majority of our atmosphere can't. because it's made of nitrogen and oxygen, which don't get lopsided even when they are vibrating. They're too symmetric. Nevertheless, the lopsided 1% are such good infrared absorbers that they manage to intercept about 90% of Earth's outgoing heat. Each captured ray gets pinged around the atmosphere, and most end up returning to the surface at least once before escaping to space. We don't need to visit the moon during frigid lunar night to know just how important the game of radiation pinball is for Earth. Ice records from our own coldest climate show that small natural variations in atmospheric carbon dioxide produce relatively big changes in temperature. They also show that, compared to the last 800,000 years, the game today is much, much harder. Thanks so much to the great team over.
Okay, so that was that video. And then before I show you the lab demonstration, just kind of take a minute and write down what your hypothesis would be on page 75. I'll give you a minute or two to do that. You'll just need to use that to answer a question on page 78. All right, so I'm gonna start the lab demonstration. It's quite a bit different from the procedures that are written in your lab manual. Your lab manual describes using baking soda and vinegar, like your basic volcano eruption. You can't really see that, and it would have been pretty awful to watch. So we changed it to incorporate dry ice so you could actually see the CO2 forming.
In this video, we're going to be doing a demonstration of Lab 9 for ENVS 100, greenhouse effect. So for our demonstration purposes, we have two flasks, each with a thermometer or a digital temperature logger inside of them. So one of these flasks is representative of the Earth's natural greenhouse effect, and that will be our control flask. In our other flask, we have an environment that will be representative of Earth's greenhouse effect when it is enhanced by
hold on, let me restart that for you guys. Hopefully it should be better now. Could you guys hear anything for the first two videos? Okay. All right, let me restart this one and hopefully it'll be better. Let me know if it's still cutting out. I can change Wi-Fi's or.
In this video, we're going to be doing a demonstration of Lab 9 for ENVS 100, greenhouse effect. So for our demonstration purposes, we have two flasks, each with a thermometer or a digital temperature logger inside of them. So one of these flasks is representative of the Earth's natural greenhouse effect, and that will be our control flask. In our other flask, we have an environment that will be representative of Earth's greenhouse effect when it is enhanced by a greenhouse gas, namely CO2, carbon dioxide. All we have inside of these flasks are just some tap water to start. And we're going to go ahead and add our CO2 in this experiment in the form of dry ice, which is just solid carbon dioxide. And the reason that we're using dry ice is mostly for the sake of visualizing the carbon dioxide. In the standard lab manual for ENVS 100, it is currently written out that we would be making carbon dioxide by mixing vinegar and baking soda. This is another great way to create CO2 gas. However, it's not as easily shown in our video. There we go. So, all of that fog right there, that is actually carbon dioxide. And you can see how it is flowing out and dripping down from the lip of the beaker, as it is indeed heavier than air. Okay, so let's go ahead, plug our temperature sensor in here, and we would expect the CO2 environment to start off a little bit colder since we just plopped some dry ice in there. Right now, our CO2 environment is sitting at 22.3 degrees Celsius, while our control environment is sitting at 24.5 degrees Celsius to start. All right, with those figures in mind, let's just go ahead and do a double check to make sure these are both well sealed. But with those starting figures in mind, go ahead and flip the light on and start recording data. That concludes our 15 minutes of data collection. Data will be exported and made available to you on Canvas as an MS Excel file. In addition to raw data, 2 columns of data have also been calculated for you. They are change in temperature of a control environment and change in temperature of CO2 enhanced environment. They are calculated by simply taking the temperature at a given time and subtracting the starting temperature from it. You'll use this data to create graphs and respond to questions for your lab assignment.
Okay, so that was that one. Hopefully it was a little better for you guys and you could actually hear it. So there's only 2 more things that we need to go over, and you'll use that video to answer questions 1 through 4, and make sure that you actually answer It's kind of small and just kind of at the bottom. But make sure down here you actually answer question 1. It's pretty easy to miss that. I'll go over the website that you'll use for question 5 right now. So for that, you'll have to get this past month's concentration of CO2 and then the year that you were born in. And then also, I think that might be it actually. You should be given the values for the others. But so you'll just use right here. You can March 2020, you'll use that one. And then to search the year, let's see, I can't quite remember. I think you can use this search bar over here. And then you can just search, or if you go over here, you can go to historical CO2 data sets and just find your birth year. If you have any problems with that, just let me know. I can run through it exactly. But I'm gonna show you the Excel worksheets that you'll be using, and I'll run through how to make the graph. So it'll be this link right here. You're gonna use data GHG Lab. It's an Excel file. You'll just download this. Share that. So you'll come up with this page. Once again, you'll have to do enable editing. Okay. So this first column you have is time in seconds. It goes all the way up to 90 or 900. These two columns right here, control and CO2. That's what you collected in the experiment. And then these are just the change from your base, or what the temperature you started at to this temperature. So essentially it's, if you were looking at this control, it's going to be every second here, and then you just minus out your initial time at 0 seconds, and that'll give you this change. So what we want to graph is these two changes over time. So time, you can do it 2 ways. I'm going to do it a little differently at first. So just because it looks a little cleaner, I'm just going to insert a tab. To do that, you would just click here and hit insert. It'll move everything over. We'll shift them down. Okay. And so instead of doing it in 900 seconds, I'm just going to do it in minutes. So it's up to you if you want to do it in minutes or seconds. That is completely up to you. But to do that, if you just highlight these two, I'll make them in both so you can see. But if you just highlight all the way to the bottom, it's going to drag this formula and just count up the whole way. So to make the graph, we're going to do a scatter plot. You need to highlight all 3 of these columns. You can either highlight from the letters up here, or you can just start here and just highlight it all. Make sure you get these 3 labels. If not, you're just going to have to put the legend in yourself. Once again, you'll go to insert. We're doing a scatter plot, so it's just like last week's. And then you do the first one, and this is it. And then this is going to be in minutes down here. And then obviously you're going to have your temperature up here, and then these are already in there for you. You'll just have to do your axes titles on a Mac. They're up here again. Axes titles, you'll have to put both on. And then that's really it for the chart. If you were going to do it as seconds, you would just highlight those, control, and then you need to highlight this one as well. Insert, same exact thing. You'll just get a lot larger here. And then your y-axis is going to be the same as the other one. This one, it's going to be the same. Your units is just different. And so instead of going to 16, it'll go to 1,000. But that's really it. You'll just need to change your axes titles, obviously, to reflect what you're actually showing. And then you'll have to change your chart title to just be descriptive completely of what the graph is showing, so that someone who doesn't know anything about it. Hold on. I apologize. I don't really know what's going on the internet, but so your graph, your chart title should just be descriptive enough so anyone off the street can look at it and know exactly what you're looking at. So that's really it for what you need to do this week. You're going to be turning in one of these graphs. It doesn't really matter if you do it in minutes or seconds. Just make sure that in your axes title, you write the units, otherwise you will lose points, because if you don't write the units, if you just write time, that's doesn't really mean anything. So you're turning in this Excel graph, this Excel sheet, and then scans of page 77, 78, and 79, and those will be due next week. Once again, if you want to go ahead and hop off,